All right, so I want to pick up here with the second part of the answer videos. Start with number 11 here. Comparing two proportions, and we want to compare to see if there's a difference in the proportion of male and females who are willing to respond to a call for uh, donating blood. And so you can see I have 60 of the first group, 60 females. First group is females. I probably should have put that in there, but I'll just put F there, or lousy F. And then the second group is the males, and there's 100 of them. And let's see, a two-tailed test is desired. I want to do two-tailed, find the appropriate p-value for this test. So you'll notice that I have some numbers on the printout. Very nice of me to give it to you this way. There's test statistic, there's the p-value, but you got to be careful. That's the p-value for the test that was conducted in the printout. Because it was a two-tailed test in the printout, this is in fact a two-tailed p-value, and that's the answer to the question. So it's a really easy question here. However, let me talk about some things that I could do. So there's a picture, and I'll draw the picture here. There's a picture where the software, it's a really lousy normal curve here. The software drew a z-distribution and put in the value of 1.93, and because it was doing a two-tailed test, it figured out the probability in this tail, and then it came over here to negative 1.93 and figured out the probability in this tail as well. And those two tails together added up to the 0.0531. Now, the reason I pointed that out to you is because sometimes I'll say, hey, what if I really wanted to conduct a one-tailed test? What if I wanted to see if the proportion of females exceeded the proportion of males? If that's the case, then I would take that p-value here and say, well, that's a two-sided, but if in that particular case, I only want this one tail out here. And so we would have to split that number in half, and that's where answer A would have been the correct answer. So I want you to be able to, it's a skill you're going to need, I want you to be able to manipulate the p-value. I want you to be able to take the p-value that's given on the printout and make it apply for the test that you want to conduct. The software I've shown you this semester has been very kind in that it's allowed us to choose the alternative hypothesis we want. A lot of software packages, even the one we've used this semester, won't allow us to do that sometimes. Sometimes it only gives two-tailed tests or two-tailed results, and we want to do a one-tailed test. So you need to be able to know when it's appropriate to split it in half and when it's not. All right, question 2. Use the rejection region approach in alpha equal 0.10 to state the correct conclusion. So if I'm going to do a rejection region for a two-tailed test, I have to split that thing in half and get a couple 0.05s. And so I'm going to draw a z-distribution now that has 0.05 out in the tail. And I need to find that cutoff point. It's got 0.05 over here as well. And so those are going to be called the critical values or the cutoff points. So I have to go either to a z-table, or I could cheat probably and use the t-table. But you need to be able to use the table to come up with the number 1.645. Now that's a skill we learned a long time ago when we worked with normal curves. And so the rejection region here would be, we're going to reject H0 if our test statistic is further out than 1.645 or negative 1.645. In the printout, our test statistic's 1.93, which just falls over here. We're going to reject H0. That's a conclusion we're going to make. That's how you would use a rejection region to make a conclusion. Now, someone might say, well, why would you do that? Why don't you just use the p-value here on the printout and say p is low, reject the hoe? That's a lot easier, and I would agree with you. Here's why I didn't do that and why I suggested you use the rejection region approach. If you screwed up the p-value in question 11 here, if you said, hey, answer D is the correct answer, you're wrong. You would have gotten points taken off, but that would have messed you up for this one as well. I try to write questions so that making an error in a previous problem doesn't burn you twice. All right, so that's how you use rejection regions. That's how you make conclusions. Bottom line is you should be able to make conclusions using both the rejection region approach and the p-value approach. All right, moving on. Comparing two means, we want to compare the mean age of male and female purchasers of a certain product. I believe this is the Crest toothpaste data set. Use a printout in question 13. Let me slide it up here a little bit and then I'll grab my pen. All right, here we go. Use the results to make an inference concerning the difference in the mean ages of the two groups. All right, first question that you need to be able to think through is, which is the correct row to use of the printout? Which of these two rows here should I be working with? And the reason this becomes an important question is because our sample sizes are small. And what we've learned is that when sample sizes are small, we got to consider the relationship of the population variances. There's a test going on here that says the population variances are equal. Our p-value says fail to reject. There's insufficient evidence to reject that they're equal. We can't say they differ. We want to use the equal row of information. Now, I made it here in this problem, so even if you screwed that up, it won't hurt you in this problem. Positive, positive. We're going back. Didn't we just talk about this? We talked about it in the context of a paired difference analysis, but it's the same concepts. Because you have two positive endpoints, because I'm going to say the difference in the means exceeds 0, I'm going to say the mean age of the first group, the females, is bigger than the mean age of the second group, the males. And so let's just see if we have a statement. 95% of the males have ages that exceed. That's not true. We're talking about means here. We're 95% confident the mean age of the males exceeds the females. That's not right. There it is. Answer C. We're 95% confident the mean age of the females exceeds the mean age of the males. And we can't say they're equal. So answer C is the correct one. All right, question 14. Which of the following assumptions must be true for the equivariance row of the information to be correct? All right, so when we have equal variances, this is the situation that we've talked about this semester where we have all the assumptions. We need a random sample. We need independent samples. That's what this technique requires. Because we're working with small samples, the populations that we're sampling from, the ages of all males, the ages of all females must be both be approximately normal, and the variation in their ages needs to be the same. So let's see. There's the normal assumption in part A. We have equal variances in part B. We have random and independent. Yeah, we need all that stuff. Answer D is the correct answer for the assumptions. Keeping the assumptions straight is probably one of your more challenging problems at this point in the semester. All right, so let's go and move on. The p-value for the two-tailed test, that's the 0.0074. The p-value for the two-tailed test is given on the printout. This is that technique we were just talking about. If we really wanted a one-tailed test, how do you go from a two-tailed to a one-tailed? You split it in half. So if I was doing a two-tailed test, a 0.074 is the appropriate p-value to use. How do I know that? That's the old way to write not equal to. The printouts you see now actually have a not equal to sign. This is a not equal to test. This is a not equal to p-value right here. So you just split it in half. All right, question 16. Suppose you want to run a different test. What alternative should you use to determine if the mean age of male purchasers, the second group, exceeds the first? If you want to see if the second group exceeds the first, it's really tempting to say exceeds, it's a greater than, but it's not. If you want to see if the second one's bigger, we talked about comparing ages, and I said my age and your age. I'm 30 years different from you. Well, if I'm the second group, it's going to be a negative number. If I take your age minus my age, we're going to get a negative 30. That's a number less than 0. So if you want to see if the second group is bigger, you actually do a less than test. So answer B is the correct answer in number 16. All right, 17 through 19, the quality improvement. Some questions on that. K Company fills cereal boxes. Target weight is 24 ounces. We collect some data. The weights of the 5 boxes are shown. And so we're going to do some control charts. So the K Company wants to conduct a control chart analysis of the cereal weight data. Which of the following describes how K Company should proceed? All right, so when you're working with means, when you're working with the X-bar chart, there's two charts that have to come into play. There's the X-bar and the R chart. R is our range chart, which is a kind of a kinder, simpler standard deviation idea. But the thought here is one of them needs to be done first. And unfortunately, usually when we talk about this stuff, we're more comfortable talking about means, so everybody talks about the X-bar chart first. But in reality, the R chart should be analyzed first. So K Company should analyze the R chart first. If it's in control, if everything looks like it should, then we go and look at the X-bar chart. So answer B is the correct answer there. And then I have a couple of charts here that I'll show you. When I talked about the charting, I pointed out to you that, and I'm going to make this a little smaller so we can put them both on the same screen. I think that'll work. I mentioned that there's a bunch of different patterns, but I'm going to make it easy for you. Let me go get my pen. And the reason I'm making it easy is because different software uses different rules. Here's what we're going to do. We're going to say there's a control limit there and a control limit there. Here's your center line. Okay. If all the points fall between the control limits, we're going to say you're good to go. We're going to say that process is in control. We should continue using that process. Okay, so this is where we're looking. Likewise down here. Because both of the charts have points that fall within the control limits, we're good to go. And so we're going to choose an answer that says that. And again, I got to take the screen draw off so that I can move down. Now, let's go back and take a look. So the process is in control. Sometimes I break it down in terms of the two charts, and I'll talk about control for the two charts. In that case, I'd say the R chart's in control and the X bar chart is in control. Because they're both in control, we're going to say the process is in control. All right, continuing on. Give a value for one of the serial weight means. So look at the means chart, which would immediately cause concern. So let's go back to the X bar chart here. And I'll zoom in a little bit. And these numbers are kind of tough to read. Let's see if I can zoom in. There we go. And slowly scroll over. All right, so anything outside the control limits. What's this look like here? The lower control limits looks like 23.8, 893 maybe? 802. It's hard to see that number. And 24.102. Let's see. 24.07 falls underneath there. 23.75, that's the one, because 23.9, 23.975, those are both bigger. So it's a 23.75 value. That's the one that would cause us concern. All right, continuing on, 20 and 21, let's compare some variances. So this is the printout from earlier, but I decided to throw a couple variance questions on the practice exam as well. When you're comparing population means, we first need to compare the variances. What alternative hypothesis should be used to determine if the population variances differ? If you're testing to see if they differ, we're going to do a not equal to. If you're testing to see, the null hypothesis would say that they're equal, but because I asked for, I did, I asked for the alternative hypothesis, we're going to say they're not equal to test. And in this particular test, if we're testing at 0.10, and the only way I want you to approach the variances is to work with p-values. So if we're working with a 0.10, P is not low, P is high, so we're going to fail to reject. If the p-value is less than the 0.1, we could reject, but it's not. And so a fail to reject conclusion would be appropriate for question 21. All right, that's the answers. Now look, I've put here in this test, I put a formula sheet, which you're not going to use. Although if you look here, there is some sample size stuff that can help. But I'm not going to ask you to do a lot of math. We'll let the computer do the math. I used to have students do work with more math, but not important anymore. Here is something I did want to point out, and I'll make it smaller. I've included, and there's a couple different places in Canvas you can find this, but I've included a t-table, and I've included a z-table. And you should have access to both of these when you're taking the exam, because you're going to need them. You're going to need them for rejection regions and for p-values. So just make sure you're comfortable with both of those. And again, this is working with inside probability. So if you're trying to use a normal table that has a different type, that's fine. I don't really care. It doesn't matter to me which table you use, but I'm just supporting this one. This is the one I talk about. This is the one I show you in all my videos, all my lectures. If you ask me questions during office hours, that's how I show you the results. So I'm going to stay real consistent. But that is the practice exam. Hopefully that makes sense to you, and good luck preparing for the final.